Hello, my name is Professor Alan Hoffman. I'm in the Mechanical Engineering Department at Worcester Polytechnic Institute in Worcester, Massachusetts. This video is associated with ES 2501, Introduction to Static Systems, commonly called statics. This video is also part of a series of videos that link 4 introductory courses at WPI. These are ES 1020, Introduction to Engineering, which is a first-year course, and that video presents material on reverse engineering. The present video for the statics course, ES 2501, and then additional videos for more advanced courses, ES 2502, which is stress analysis, and finally ME 2300, which is Introduction to Engineering Design. Statics. Statics is the study of forces and moments acting on bodies which are in equilibrium. Therefore, we have to understand the definition of equilibrium. In equilibrium, the sum of the forces in any direction must be zero. And similarly, the sum of the moments about any axis must also be zero. The material covered in a statics course is fundamental to the successful completion of more advanced engineering courses. In particular, stress analysis in higher level courses, as well as dynamics in higher level courses, and also all design courses. Another definition of statics is that it is a study of bodies and systems that are not accelerating. Thus, the linear accelerations in all directions are equal to zero, and also the angular accelerations about any axis are also equal to zero. Statics has many common applications. Bridges are in static equilibrium. Buildings are in static equilibrium. The chair and the table I'm using to produce this video, each of these bodies is in static equilibrium. Newton's laws state that the sum of the forces equals the mass times the acceleration. These are vector equations, so they apply in all 3 directions. Similarly, the sum of the moments about any axis is in a slightly simplified form equal to the moment of inertia of the body times the angular acceleration. Both forces and moments are vectors, and linear accelerations and angular accelerations are also vectors. In statics, both of these accelerations are equal to 0. In 2 dimensions, which will be the primary subject of this video, one way of writing the 3 equilibrium equations is to state that the sum of the forces in the x direction, you must first define a coordinate system before you can apply the equations of equilibrium. So the sum of the forces in the x direction are equal to 0. The sum of the forces acting on a body in the y direction are equal to 0. And the sum of the moments about the z-axis is also equal to 0. Now these equations can also be arranged in a slightly different manner. As I described them, there were 2 force equilibrium equations and 1 moment equilibrium equation. However, you can also solve an equilibrium, a 2-dimensional equilibrium problem by using 2 moment equations and 1 force balance equation. The requirement, however, is there are only 3 equations, and thus on any free body diagram, and we'll define that next, there can be at most 3 unknowns if you're going to solve for the forces on that body. In 3 dimensions, 3-dimensional equilibrium, there are 6 equilibrium equations. But that would be subject for another video. A free body diagram. The crucial ability in both statics and also dynamics, and essentially all the succeeding courses like stress analysis and in design, is to be able to draw free body diagrams. Free body diagrams isolate a body from its surroundings and show the effects of these contacting bodies as forces and moments acting on the body you have isolated. Most forces act directly through surface contact. However, such forces as gravity, which is represented by weight, acts through a distance without direct surface contact. Now, in the problem we're going to present here, we're actually going to analyze a mechanical device that is applied really in a dynamic situation. But the accelerations in this case are essentially so small so as to be negligible, and thus this is really what we would say is a quasi-static case where the principles of statics apply, because although there are small accelerations, they are indeed can be neglected. They can be neglected. So here's our problem here. What we have here is a bottle, and here is the cap on the bottle. Now we're gonna look at a mechanism that places the cap that after you place the cap on the bottle will crimp what's called the crown here. Will crimp the crown so that it seals the bottle. Now, bottle sealing mechanisms have been around and patented for almost 100 years. They were originally used in the home to seal bottles containing products that were produced primarily in an agrarian society. Nowadays, the major application is for beverage bottles, and indeed, in terms of people who home brew beers and other beverages, the device I'm going to show you is purchasable in the current market, and its job is to put the cap on the bottle. This device, this is one version of it. Here's a bottle capper, and its primary use, as stated previously, is for capping beverage bottles in a home brewing environment. Now, how this works, and this bottle capper has been described in an earlier video, and the location of that video appears on the screen at this point, in which I discussed reverse engineering this particular device. Now, in your ES2501 lab, you will have access to this device in its intact form, and also in where the pins connecting the rotating joints here, which probably are a little more visible over here, have been replaced by long bolts, so you're actually able to disassemble it and get a better look at the object. Now, in statics, what we're going to do, and I'll demonstrate it briefly, is how this works is you put it on top of this device, or you might indeed put the cap in the device itself, because there's a little magnet here which may or may not work that well, and then you clamp down on the cap and bottle like this, and then you bring your hands down. Now, up to this position, I'm not really exerting any forces, but then you can see my hands about where they are in the position on the bottle capper, and then I squeeze down and exert the force to crimp the cap, the crown onto the bottle. Now, I've done this on a number of caps, and the average force, if I do it in a quasi-static manner, just slowly crimp down, the average maximum force is about 55 pounds. However, if I get a little more aggressive in doing this, the total force will come out to be about 75 pounds. If I get more aggressive, I have the potential of shattering little pieces of glass off the lip on the bottle. So hopefully I will be able to demonstrate this carefully. Put it on like that. Oops. Okay, yes. And then gradually, slowly come down. Do that. You saw that I went down slowly, so that was quasi-static, and then if I can get it up, and then get the bottle out, which didn't work. There it is. There it is. A little difficulty getting it out from the. So essentially that's the problem. And your job in statics is, given these forces on the hands, note that my total force, which I described, is evenly divided by my hands, but its direction is not perpendicularly down. It's generally perpendicular to the handle as I work it down. So you'll be asked to look at this in particular positions. You have access, as mentioned, to the prior video on reverse engineering. You'll have the bottle capper that has screws and bolts and nuts on it, so you can actually take these apart. But your job is to figure out how the forces in my hands are transmitted to create an unknown force, from your standpoint, that presses downward on this bottle cap and then essentially causes it to crimp. You have access to a full set of drawings on this, produced by one of my assistants, produced by Michael, whose name is on the title slide of this video. And your goal, again, one more time, is to understand and calculate the forces that are transmitted through each component of this bottle capper as I undertake the action to place the crown on the bottle. Thank you very much.